Welcome back. So let's move on to another interesting algorithm, which is density estimation for mixture distributions. See, one important question is when we do maximum likelihood estimation, we will start by assuming that our underlying density has a particular functional form. We just saw one case where we assume that to be a Gaussian density. Suppose our true density function, okay, was like this. So this is our this is x, which is our random variable, and this is the px, which is the density that we are trying to estimate. And I am writing it in one dimensions because I only have a 2D sheet to write. Typically this is the densities that we are talking about is in 10,000 dimensional space and all that. I mean, it's in RD. So let's say my density was like this, and let's say that I start my ML estimation by assuming that the underlying density is a Gaussian distribution. Now what is the degree of freedom that I have? So I have already made a assumption on the functional form of the underlying density, which is that it's a Gaussian. Now I can only control amongst all possible Gaussians that are out there, which Gaussian will minimize the KL divergence between this and the between itself and the true distribution that I am considering, correct? Now if I am assuming that the underlying density is Gaussian density, no matter what I do, I cannot make my KL divergence lower. Why? Because all I can do, I can place my mean here and make my variance very large. This is one estimate, right? The other estimate can be that, oh, I will fit this particular mode and then do this. Do you see what I am saying? None of these estimates, the other can be, I can make my Gaussian density here, fit this mode and then go here and so on. See, no matter what I do, my ML estimate will not be good. Why? Because I have made a bad model assumption. See, again, giving an analogy, I mean, if we take a parallel to the empirical estimate minimization framework, let's say that we are looking at a like a quadratic function that is our underlying hypothesis. If I assume my h theta to be a line, no matter what I do, I cannot get close to the reality because I am constrained by my model. I made a no matter what the parameters of my model is going to be, if I start with a bad model assumption, then I cannot make my KL divergence arbitrarily low. Do you see the point? In general, univariate density functions are not good estimators. Sorry, not did I say univariate? Not univariate, unimodal. Unimodal density functions are not good model choices because mostly in practice the densities that appear are not unimodal, they will be multimodal. Okay, what do you mean? What, by the way, what do you mean by mode of a density function? Not defined it. Assume that you people know it. It's the point where the derivative of the density function vanishes. For Gaussian density, there is only one mode because that's the only point where the density vanishes. The derivative of the density vanishes. Now, if there is the underlying density has multiple modes, then no matter what parameters you choose, okay, over the ML estimate, using the ML estimate, you are going to get a bad estimate because the density assumption itself is wrong. I mean, uh, wrong. I mean, I didn't say that. There's no way that you can say it's right or wrong. It's a bad model in the sense that the KL divergence when we compute between these two, it will be pretty large. Okay, so a better model assumption has to be made. You had a question? Yes.
How can we assume that PX is mixture of Gaussian? That we don't know. So PX is we don't know anything about PX, right? So
No, did I even utter the word mixture of Gaussian so far? I am only saying that this is not a mixture of Gaussian. These are different Gaussians. All I said so far is that if the underlying density has multiple modes and you start with the initial, if you make your p theta to be a unimodal density, then no matter what ML estimation you do, you are going to get a very large KL. This is my statement. Does it make sense? Any questions on this? Okay. This is just to motivate that unimodal distributions cannot be good models. So what do we do? Yes.
so that will happen no matter what model we choose because the absolute
Good. Good point. Yeah. So what the question that is asking is the fact that the KL divergence will be large between the reality, the true distribution and the model distribution will be large no matter what model we assume. Correct. I agree. But you can compare two models. No, if you can make a model assumption that will lead to a lower KL compared to another model, you would always take the model that leads to lower KL. Here in this case, suppose the underlying density is multimodal. No matter what you do, you cannot take a unimodal density and make the KL divergence arbiter law. The question that we are asking now is there a better model? Is there a better model for the case where the underlying density is multimodal, which is often the case?
It can overfit as well, right?
Did I say what overfitting is? Not even uttered the word overfitting yet. We'll get to that. We'll get to that. Okay. Is that okay? So I am just giving you another choice of a model. So right now we only have we have only seen densities that are unimodal. We'll give you a choice for a density function that has multimodal nature in, I mean, by construction. That's it. Okay. So let's look at that example. Which is so multimodal densities are not well estimated. See, when I say well estimated, I only mean in the sense of minimizing KL with unimodal models. Solution, try a multimodal model. When I say model, I am talking about the p theta or the density that we are assuming, right? Now, if you take a unimodal model or density, we only have choices on their parameters. So, if you take Gaussian distribution for instance, you can control where is it centered and what is the spread. If you take a multimodal model, right, then you can perhaps control many other parameters. Okay, so now how do you define a multimodal model? How do you define a multimodal density is the question. So one example is what is called as a mixture density. So now here, if suppose V is a random variable which is in Rd. So we define a mixture density as follows. Now p theta on V is defined as 1 through m alpha j p notations p theta j evaluated at V. Okay, I will say j here, where just define what these are. So where alpha j's are numbers between 0 and 1 and p theta j is a density function. Now this is called a mixture density model, where the density function is taken to be a linear combination. In fact, it is a convex combination, as we will see. It is a linear combination of m other density functions. You see this? See, I am not saying that the value that the random variable takes is a combination of something. It has nothing to do with the random variable. I am just saying that the density function is a linear combination of m other density functions. There are j density functions, sorry, m density functions, and you take a linear combination of m density functions to get the final density function. This is called a mixture density function. And do all of p theta j be of the same functional form? No, not necessarily. It can have different functional forms, meaning you can one of the densities can be Gaussian, the other densities can be other density can be exponential and so on, but typically it is chosen to be homogeneous. You take the same density functions and take, and what is m here? M is the number of density functions that you are combining. That is also a knob that we can play with. That is also a model. It's not a parameter, it's called a hyperparameter, because see, what is the difference between a parameter and a hyperparameter? Parameters are the one that we find out by solving the underlying optimization problem. Hyperparameters are the ones that we just choose, okay, without optimizing them explicitly. Here, for instance, the number of mixtures that you would take to construct a density function, the mixture model is a hyperparameter, and the choices of the individual densities that you make is also a hyperparameter and so on. Okay, I'll be using this term parameter and hyperparameter. So yeah, you understood. So there are, see, suppose you choose one special case of this is what is called as a Gaussian mixture model, GMM, where the individual densities, all p, theta, j will be Gaussians, okay, with the parameters theta j. So if you take j Gaussian densities and take linear combinations for m Gaussian densities and take linear combinations of them, then the underlying mixture density is called a Gaussian mixture density or Gaussian mixture model, GMM. Alright. Now you asked that question, right? Isn't it the case that you take any underlying model, then it will not be arbitrarily close? But why do we choose mixture densities like this, especially the Gaussian mixture densities, is that there is this very powerful theorem which I will state without proving, okay, as a matter of fact, is that GMMs are universal density approximators. So you take a continuous random variable, you take any density function, you can always find a GMM. What does this mean mathematically? You know that epsilon delta definition for closeness of functions, right? I am assuming that you people know what it is. So take a density function which is defined on a continuous random variable, you can always find a Gaussian mixture model that would make the KL divergence between this GMM and the underlying density arbitrarily close. That is what this theorem is telling. Does it make sense? So all I am saying is that you can always find a GMM, okay, that will bring the KL divergence between the data or the true distribution and the model distribution arbitrarily closely if you execute it well. Is this okay? This is the statement. Yeah, questions? Come again? I didn't get the questions. All I'm saying is you can always find a GMM that explains your data in the sense of minimizing KL divergence.
There might be a mixture model which can minimize the KL divergence even more than for that particular case.
Possible. See, but practically what do we do? The question is, why do we choose GMMs is the question, because at least we know that the GMMs are universal density approximators, so that we can hope to choose a GMM and get our KL divergence arbitrary close the two lower values. But remember this, there is no way on earth that we actually measure the true KL divergence that we are trying to minimize, because we do not have access to distribution at all, right. So I have still not answered this question, right. Suppose after you build a model, how do you evaluate it? I will answer that in the coming classes, but all I am saying is that if anyway you are modeling, you start with a model that has better capabilities, and that is why you start with GMMs, that is it. Yeah.
GMMs are this powerful. Why is it that we would want to resort to anything other than?
Good question. I thought somebody would ask. See, the question that is being asked is, machine learning should end with GMMs, because what else is there, right? You know that the base classifier is optimal, and you know that the GMMs are universal density approximators. Done. Given a problem, learn a GMM, get the parameters, estimate, I mean, put down a base classifier, that is it, right. It is a very valid question. In fact, I would have asked this question myself after GMMs are done. So the course should stop at GMMs, right? Why are we even going further? Maybe I'll take it later when we complete how to algorithmically learn solve the problem. I mean, estimate GMM's parameters. But since you have asked, there is something called curse of dimensionality, which I will talk about. The idea is that these algorithm, theoretically what you said is correct. Theoretically speaking, if you can estimate the parameters of GMM, then it's done. But typically the space, the dimensionality of the space that we operate in is very high, right? You saw, even if you take an image, it is some 40,000, 50,000 dimensional space and so on. In those kinds of dimensions, the algorithm that we will see right now, which is the standard algorithm to find the parameters of the GMM, will get stuck to a local optima, which is not correct. We will see that. So there is an algorithm called the expectation maximization algorithm, or EM, is the algorithm that we will use to, it's actually maximum likelihood estimation for GMM is EM. So we cannot do it analytically, we will have to do it iteratively. We will construct an algorithm that would solve the maximum likelihood estimation problem for a large class of models of which GMM is a member. So EM is a generic algorithm that we will see right now. It's called the variational inference algorithm, which we will see. See, EM is a special case of variational inference. And one other example of variational inference is what is called as a variational autoencoder, or also this diffusion models which are currently used to generate images within these AI models. Same class of algorithms will be applied to estimating parameters of GMM and to build a variational autoencoder and to even generate that Ghibli image that you do today. So we will see that algorithm in the next class. To your point, these algorithms are numerical and there is this thing called curse of dimensionality that would not let a GMM maximize the likelihood or minimize the KL divergence in high dimensional spaces, and that is why it does not stop there. But it is a great question. Actually it should have been theoretically, yes, given a problem, resort to base classifier and fit a GMM and then you are done. In fact, the first of your assignments will be this, that you will be asked to code up EM, right? That is what we will do. Okay, so GMMs are universal density approximators and that is why they are good models of Gaussians. You can take, there are nonlinear combinations of densities as well, but it is like this. The question is why only linear combination of densities. So you can compare this with the Fourier transform or Fourier series. In Fourier series, you take linear combination of sines and cosines, exponential functions, to estimate any periodic function to arbitrary closeness, right? What are these? These are basis functions, right? So if you have a vector space and you need to if those basis vectors have to span the entire space, you will have to take linear combinations of them. That is exactly the thing. So Gaussian densities, because of their infinite support nature, form the basis for the space of Hilbert space that contain all density functions. That is what I am saying. Look into Gaussian densities as basis functions for the space of density functions. So you can take multiple Gaussians and take linear combinations of them and get to any density function in the space of density functions. That is it. Just like you have the exponentials, right, in the Fourier series case, the Gaussian densities exist. So I wanted to stop this class at one other algebraic point leading to EM algorithm. Can I extend by 5 more minutes? Yeah, just this class maybe. Yeah. So what happens is when you write the likelihood function for the density, so if suppose p theta, maybe I will just say this and do the algebra next class because anyway I will have to do it next class. What happens is, if you write down the log p theta, which is the likelihood function for the Gaussian density, see all this while what was happening, we had log of some function, isn't it, log of p theta. If this p theta comes from the family of exponential densities, then this logarithm and this exponentiation gets cancelled off and you get a function in the random variable and the parameter which could be differentiated and put to 0. But now if you have a mixture density, instead of having sum of logs, you will get log of sums because p theta involves a sum. So log of sum and within that sum, if you have an exponentiation, this log and that exponentiation will not cancel out with each other, and therefore if you differentiate that and put to 0, you will not get separated terms, terms that are separated out in terms of parameters of individual Gaussians. And therefore this optimization problem cannot be solved if you have log of sums instead of sum of logs. I wanted to write that algebra, but it is obvious, right? So if p theta has sum of e power exponential functions, then log of some exponential functions, this log will not cancel it out, and therefore you cannot differentiate and put to 0. Therefore we need to resort to a numerical way of solving this, which is what the expectation maximization algorithm is all about, where the idea is to create a bound, okay, a lower bound on the objective function, and instead of optimizing the objective function directly, you iteratively optimize the lower bound of the objective function, which is the likelihood function this time. We will see that the next, why we will look at the correctness of that algorithm, and also we will see that algorithm working for GMM. Okay, so this completes this particular class. Please remember the overall story, because if you get deeper and deeper into the algorithmic nuances, it seldom happens, it often happens that you remember what's happening. We are estimating density functions, and why are we estimating density functions? Because we want to implement the base classifier. Okay, why should we implement the base classifier? Because we need to minimize the risk, and this is the best classifier that we can implement. Okay, see you next class. Thank you.